Hi folks, welcome to this chapter. We'll be looking at chemical bonds and compounds. Now, the first thing that we are going to look at the Lewis structures and the octet rule. First of all, before we start, we need to know how a compound is formed. If we know how a compound is formed, it will be easier for us to know how to form compounds and how to balance chemical equations that involves compounds. So the very important thing that you should know is that for a compound to be formed, only the valence electrons are involved in the interaction. So all the properties of the compounds that you will see is based only on the valence electrons of the elements that make up those compounds. So there are those valence electrons that combine, or they are responsible for the reactions of those elements. So the valence electrons are the electrons that are found in the highest occupied energy level, or the electrons that are found on the outermost shell of an element. Now, we are going to be looking at the main group elements here, and for the main group elements we are looking at the group 1A, group 2A, group 3A, group 4A, group 5A, 6A, 7A, 7A, and 8A. They are also called group 1, 2, 3, 4, 5, group 1, 2, 13, 14, 15, 16, 17, and 18. So for these main group elements, there are only the S and the P subshells that are involved. And the S subshell can hold a maximum of 2 electrons and the P subshell can hold a maximum of 6 electrons. So generally, they can hold up to 8 electrons. Now I will show you an example. For us to know how many valence electrons are found in an element, we need to just identify the group of the element in the periodic table. For example, hydrogen is found in group 1, so it will have 1 valence electron. Lithium is found in group 1, so it will have 1 valence electron. So if you look at beryllium here, beryllium is found in group 2, so it will have all the elements of that group will have 2 valence electrons. Boron, aluminium, they are found in group 3, so they will have 3 valence electrons, and so on. So if you look at neon or helium, they are found in group 8, so they will have 8 valence electrons. So that is how you identify the number of valence electrons in an atom. Now, let's look at, for example, nitrogen here. Nitrogen has 5 valence electrons. So for those 5 valence electrons, 2 of them are S and 3 of them are P. So the first 2 electrons will be the S electrons, and the last 3 will be the P electrons. Now for neon, neon has 8 valence electrons. Everything that we are looking at here are the valence electrons. Neon is found in group 8, so it has 8 valence electrons. So it will have 2s and then 6p. That makes 8. Now let's continue with the Lewis structures, the Lewis symbols, and how we can show the valence electrons using the Lewis symbols. Now I will show you what Lewis symbols are. So Lewis symbols are the Lewis dot symbols, okay? So they represent the valence electrons as dots around atomic symbol. For example, we have lithium. Lithium is found in group 1. So if we want to draw the Lewis symbol, we'll write lithium, that's the symbol for lithium, with 1 dot, which represents an electron. If we want to write for a group 2 element, for example, beryllium, it will have 2 dots, which represents 2 electrons. So those are the valence electrons that we are talking about here. If we are looking at, for example, boron is found in group 3, we have 3 valence electrons. So that is the Lewis symbol. For carbon, carbon is found in group 4, we have 4 valence electrons, so 4 dots. For nitrogen, nitrogen is found in group 5, you have 5 valence electrons. For oxygen, it is found in group 6, and it will have 6 valence electrons. Fluorine is found in group 7, and it will have 7 valence electrons. And neon is found in group 8, so it will have 8 valence electrons. So these are the Lewis symbols, and they show us the number of valence electrons. Now, let's look at what we call the octet rule. What is the octet rule? The octet role is an atom is stabilized by having its valence energy levels filled. So the octet role states that for an atom to attain the octet role, it must have a filled energy level. So for example, fluorine, for it to attain its octet, it must have 8 valence electrons. For oxygen to attain its octet, it must have 8 valence electrons. For nitrogen to attain its octet, it must have 8 valence electrons. So how do these atoms attain this octet role? Now remember that the noble gases, they are found in group 8. So they have 8 valence electrons and they are already filled. So they already fulfill the octet role. Now for other atoms to fulfill the octet role, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and all the other atoms in the main group elements, they will either obtain the octet by gaining or losing electrons. So when they gain or they lose electrons, they form what is called an ion. And we will see 2 types of ions, the positive ion and the negative ion. So they can also attain the octet by sharing electrons. For example, the group 4 elements, carbon for example, it will attain the octet by sharing electrons. Lithium, beryllium, boron, they can attain the octet by losing electrons, and fluorine and oxygen, they will attain their octet by gaining electrons. So when a species gains or loses electrons, it forms what is called an ion. So an ion is an atom or a group of atoms that have an overall charge. Okay, here on the periodic table we are looking at the hydrogen ion here, the lithium ion, the beryllium ion, the sodium ion, the magnesium ion, and we are also looking at the aluminum ion. So this is for metals, all here, the group 1 and the group 2, those are the metal ions. Here we have the transition metal ions, and the transition metal ions, they always have more than one ion that they form. So they form, some of them form more than one ion. And for the non-metal ions, we have the nitrate, phosphide here, oxide, the sulfide, the chloride, the fluoride. So these are the anions. We call the negative ions the anions, and we call the positive ions the cations. So these are ions. Now let's see how the cations are formed. Like I just showed you, the cations are the positively charged ions. Let's take for example sodium. Sodium is found in group 1 and it has 11 protons or 11 electrons. So if you write the electronic configuration of sodium, it will be 281. So it means that its valence electron is found in the 3rd energy level. So it has 1 valence electron. Now for sodium to form an ion, it has to lose that valence electron. So that is what this is, the sodium atom, and here is a sodium ion. It has lost that 1 electron. This electron has been lost, and here you have a sodium ion. Now when the sodium atom loses an electron, it becomes a sodium ion and it fulfills the octet, because now you see that the octet, now the outermost shell here contains 8 electrons. Okay, and when that happens, it resembles the noble gas that is closest to it, which is neon. So here in this case, oxygen and neon, they have the same electronic configuration and they both fulfill the octet. So in the case where they have the same electronic configuration, we say they are isoelectronic. So sodium ion here and the neon, they are termed isoelectronic. Now let's look at the Lewis structures, how they show cation formation. I just showed you how the sodium atom formed the sodium ion. Now let's use the Lewis structure to show how that happens. So for the Lewis structure or the dot structure, we said the atom, we show the electron in the valence orbital by a dot. So sodium here, it has just 1 valence electron, so that is 1 dot. What will happen is that sodium is going to lose that 1 electron, So when it loses that one electron, it forms the sodium ion plus an electron. So that's a balanced equation. That's how you write it. Now, we see that sodium here, the electronic configuration shows that in the 3s orbital, it has one electron. So when it loses that one electron, it now has the same electronic configuration like neon. So I said that is called isoelectronic. Now let's look at another element. Let's look at the group 2 element now. Let's say we look at magnesium. Magnesium is found in group 2 with 2 valence electrons. So the 2 valence electrons, we are using the dot, the Lewis structures or the dot structure. We see here that it has 2 valence electrons. So for it to obtain the octet, it has to lose 2 electrons. So it loses 2 electrons to form the magnesium 2 plus. So the number of the 2 here shows you that it has lost 2 electrons for the charge. Please never forget, when you see that charge 2 plus, it means that it has lost 2 electrons. If you see a charge of 3 plus, for example, aluminum, it will mean that it has lost 3 electrons. Now, you will also see for anions. So here we have the group 1 and the group 2. So all the group 1 elements, for them to attain an octet, they will have to lose 1 electron. So when they lose an electron, they become positively charged, plus. Now for the group 2, for example, we've seen magnesium. That's the same thing that will happen for beryllium, same thing that will happen for calcium, and the same thing that will happen for strontium. So they will lose 2 electrons to obtain an octet. So the transition metals, they also form cations, but the cations are not always single. Like you may have chromium, which is, they have chromium 2 and chromium 3. So the cations, the typical charges for the cations are, they range from +1 to +4. Now, some metals form multiple charged ions, and the p block metals also do this. For the p block metals that also do this, remember everything here is the p block. Everything here is a p block. So for the p block metals that also do this, we have this. We have tin and lead. So we have tin 2 plus here, and we have tin 4 plus. We have lead 2 plus and lead 4 plus. So let's see how we can name cations. We've seen the cations. Let's now see how we can name them. So metal cations have the same name as the neutral metal. For example, if I'm talking about sodium, you will hear, we will say it's a sodium ion. If we are talking about magnesium, we will say it's the magnesium ion. Take note, when we get to the anions, it will not be the same. So here we have other examples. For example, we have iron and copper. There are 2 conventions. There is an older way of naming them, and there is a modern way. For example, if we are looking at iron, for iron 2, the older name will be called ferrous, and iron 3 will be called ferric. Now for copper, the older name for copper 1 will be called cuprous, and copper 2 will be called cupric. Now let's look at the modern name. How do we call this iron 2 ion? We call it the iron 2 because it has lost 2 electrons. For the other ion that has lost 3 electrons, we call it iron 3. Same thing for copper. Copper 1, it has lost 1 electron, so we call it copper 1. And the copper 2 has lost 2 electrons, we call it copper 2. So this is how we name the cations. Now, let's practice naming these cations. So name the following cations. You can pause the video here, and then you name them. Okay, now the first cation, that is for silver. If you look on the periodic table here, silver has just 1 cation. So you see it will just be silver 1. So for lead, here lead has 2 cations. So it is going to be lead 2 and lead 4. So this is how you name the cations. Now let's look at the anions. We've looked at the cations. Cations are formed when atoms lose electrons. Now, anions are negatively charged ions, and they are formed when atoms gain electrons. So all metals will form cations, and all non-metals will form anions. So what you see here, this is the P block, which consists of the non-metals. So the non-metals will form anions. Now, anions fulfill the octet role. So as the cations fulfill the octet role by losing electrons, we will see that the anions, they will fulfill the octet role by gaining electrons. Okay, now let's look at, for example, fluorine. If we draw the Lewis structure, the Lewis symbol for fluorine, fluorine is found in group 7, so it will have 7 valence electrons. So if you write the electronic configuration, this is what you will see. Now, it gains 1 electron, and when it gains that electron, it forms a fluoride. Okay, so in this case now, it has gained 1 electron and it is called a fluoride. So all the group 7 elements, they gain 1 electron to attain the octet. And for the group 6 elements, all of the group 6 elements, we have oxygen, sulfur, selenium. All the group 6 elements, they will gain 2 electrons to attain the octet. For the group 5, that will be the same. The group 5 will gain 3 electrons to attain the octet. Now let's look at how oxygen, for example, which is found in group 6, how they attain the octet. Oxygen, if you draw the Lewis symbol, oxygen is found in group 6, so it has 6 valence electrons. So it's going to gain 2 electrons and it will form an oxide. Remember, I told you when we are naming cations, the name does not change. But for anions, the name changes. It will be ending with IDE. Oxygen will be oxide. Fluorine will form the fluoride. Now, this is how the non-metals, they gain the octet. They attain the octet. The group 7A, they will gain 1 electron. The group 6A, they will gain 2 electrons. And the group 5A, they will gain 3 electrons. So that is how you write the ions for these groups of elements. Now, let's see how we can name the anions. We have to change the ending to IDE. For example, the first atom here, we have chlorine. The anion will be Cl- because it's in group 7. You need just 1 electron to attain the octet. So when it has that 1 electron, the anion name is going to be called chloride. It ends with IDE. Now for oxygen, oxygen is found in group 6. So for it to attain the octet, it needs to gain 2 electrons. So the oxide, you will see, it will be O2-, which means it has gained 2 electrons. The anion name will be called oxide. For sulfur, sulfur is also found in group 6, so it will gain 2 electrons. And the name of the anion will be sulfide. For nitrogen, nitrogen is found in group 5, so it needs to gain 3 electrons to attain the octet. So the name of this, the anion symbol is N3-. The name of the anion is nitride. Alright, so let's look at what we call polyatomic ions. From the word polyatomic, it means that it is more than 1 atom. So polyatomic ions are groups of atoms with a charge. Okay, these are groups of atoms with a charge. Now, one thing that I will let you know is that we see so many of the polyatomic ions here with a negative charge. The only polyatomic ion that has a positive charge that you must remember is the ammonium ion. So that is the only polyatomic ion, the cation. So that is the only polyatomic cation. All the other ones are the polyatomic anions. Here, for example, if you look at the nitrate, you see it has 3 oxygens with a charge of -1. You have the nitrite, 2 oxygens with a charge of -1. So you have to take note of the number of oxygen atoms here. So one thing that you have to know is to try to remember these polyatomic ions. I've said the only polyatomic cation here is the ammonium, but we have so many polyatomic anions. Make sure you master this. We have the nitrate, the carbonate, the bicarbonate, we have the phosphate, and take note of the charges. So you have to memorize these polyatomic anions. Now, let's continue with these polyatomic anions. And here, we'll be looking at other polyatomic anions that are called oxyanions. When you hear of the word oxyanions, these are polyatomic ions that contain an oxygen atom in their structure. Now, they are usually named as the element road plus ATE, depending on the number of oxygen atoms. So if we have 3 oxygen atoms here, for example, for carbonate, we are going to name it carbonate with ATE. Now for phosphate, phosphate will have 4 oxygen atoms, so we are going to call it phosphate. I'm stressing here because we will see oxyanions with multiple number of oxygen atoms containing the same elements. The number of oxygen atoms vary. So for these ones, the carbonate and the phosphate, they are just these ones. In the case of like the nitrate, you will see that we will have the nitrate, we will have the nitrite, so it will be different. So master this. Now, for more than one oxyanion, like I've just told you, for example, we have these two. The first one is called the nitrate, and the second one is called the nitrite with ITE, not IDE as we were naming the anions. So ATE for more oxygen atoms here, so nitrate. Then ITE for fewer oxygen atoms, we have nitrite. So this is how you name the polyatomic ions. Now, this is another example. For more than one oxyanion, we will either have ATE for more oxygen atoms and ITE for fewer oxygen atoms. Now, we are going to look at the case of the chlorate here. We will see the chlorate, which is the one with the 3 oxygen atoms. The one that has 2 oxygen atoms will have the chloride. The one that has 4 oxygen atoms, we'll call it the perchlorate. Per means that it has more oxygen, one more, perchlorate. Then when it has one less oxygen, we are going to call it hypochlorite. Now, these are the ions that you have to know. For these ions, we've already talked about these cations. We've talked about these anions. We've also talked about these ions and these polyatomic ions. So you need to know all of these ions here. Now let's look at ionic bonds and compounds. So how do compounds form? When we hear of ionic bonds here, we have said that ions are formed by having a charge. So when we have 2 ions of opposite charges, what happens? They will attract each other, and when they attract each other, they form an ionic bond. So an ionic bond is an attraction between oppositely charged ions. So there is an ionic bond here, and when this happens, they form a compound, and that compound is called an ionic compound. So an ionic compound is composed of charged ions. We have a positive and negative charge, so they form an ionic compound. Metal cations and non-metal ions, they form the type of compounds that we call ionic compounds. For example, we have sodium chloride. If you look at the example here, like sodium chloride, we have magnesium chloride, we have lithium chloride. So all of these, they are formed between the cations and the anions. The cation here will be sodium, the anion here will be the chloride. The cation here will be magnesium, and the anion here will be chloride. So these are ionic compounds. Please master this, as opposed to covalent compounds that are formed between 2 non-metals. So when compounds are formed between a metal ion and a non-metal ion, they are called ionic compounds. So here we have a lattice. So a lattice, an ionic lattice, is an array of positive and negative ions. So here in this structure, in this lattice, we have the ionic, we have the positive and the negatives. So the positive, the anions, the cations, which are positive, are always smaller than the anions, which are negative ions. One thing, the cations will most of the times always be smaller in size than the anions. So let's look at what we call the chemical formulas. Now, the chemical formulas, they show the type and amount of each element present. For example, I just showed you sodium chloride. That is the chemical formula for sodium chloride. It shows you which type and the amount of the element found in that compound. Here, let's look at what we call empirical formula. The empirical formula is the smallest whole number ratio of atoms. Okay. We also have what we call molecular formula as opposed to the empirical formula. So the empirical shows the smallest whole number ratio, and the molecular formula will show you the actual number of each atom that is found in the compound. Now, sodium chloride here is a formula unit. What is a formula unit? A formula unit is the smallest number of ions necessary to form a compound. So for you to form a compound between sodium and chlorine, you will need one sodium and one chloride. That is called a formula unit. Now another example, for you to form a formula unit of magnesium chloride. So magnesium chloride, you will need one magnesium ion and two chloride ions, because the charges must always be neutral. So this is a formula unit of magnesium chloride. This is a formula unit of sodium chloride. So the sodium is the cation and the chlorine is the anion. Now, let's look at ionic compounds. How we can write the formula for a compound that is composed of potassium and sulfide ions. The potassium here is the cation, the sulfide here is the anion. Now, the first thing that you have to do is to know the charge that each of these atoms carry. For the potassium ion, it has a charge of plus, and the sulfide ion has a charge of 2-. One thing that you should always remember is that for a compound to be formed, the charges must balance out. They must cancel out. So the number of positive charges must be equal to the number of negative charges. So for example, for this compound to be formed between potassium and sulfide, the charge on the potassium is 1 and the charge on the sulfide is 2-. So we see that we have 2- charges and we have just one positive charge. So what are we going to do? We need to add one more potassium. So that has to cancel out the charges. So now we have 2 positive charges and 2 negative charges. So the positive charges must be equal to the negative charges. Now we are forming our compound which has a neutral charge. That gives us K2S. K2, 2 of the potassium and 1 of the sulfide. So the total charge is equal to 0. Now let's look at another example, the compounds with polyatomic ions. So write the formula for a compound composed of calcium and nitrate ions. First thing, you must know the group of the calcium, and you must remember the formula of the polyatomic ion, the nitrate. So let's see. The calcium ion has it has a charge of +2, and the nitrate ion, it has a charge of -1. So for charge to be balanced, we need 2 of the nitrates. So 2 of them and 1 calcium. You see that the charge will balance out, and the formula of the compound will be CaNO3 2. Remember, we have bracketed the nitrate because it is a polyatomic ion. The 2 here is for all of them, for everything inside that bracket. So the 2 here we have, if you want to look at the number of atoms here, we have 2 times 1 for nitrogen, which is 2 nitrogen. We have 2 times 3, which is 6 oxygen. So that bracket, the what you see outside the bracket affects everything inside that bracket. Now, let's look at another compound that is composed of aluminum and the sulfate ions. Aluminum is found in group 3, so it has a charge of 3+. The sulfate is SO4 2-. Remember, I've told you have to memorize the polyatomic ions. The sulfate is the 2-. Now, if we look at the charge, we see that aluminum has 3 and sulfate has 2. Now, what can we do? The easiest way for us to solve this problem, I will show you just now, and you can apply it even to the ones that we have solved. The best way to do is to cross multiply the charges. You see that if you multiply aluminum by the charge of sulfate, you will see that it will be 3 times 2. It means that you are going to need 2 of the aluminum. Now for the sulfate, the charge is 2 minus. You multiply by the charge of aluminum, that will be 2 times 3. It means that you are going to need 3 of the sulfate ions. So in this case, all of them will give you 6, meaning that the charge is neutral. So we need 2 of the aluminum and 3 of the sulfate. So that forms a compound. And remember, the sulfate is a polyatomic ion. We must always bracket the sulfate and then put the number of the sulfate ions outside the bracket. So this gives us the formula with 2 aluminum, Al2SO4 3. So that 3 outside shows that it is for everything inside that brackets. Now let's see how we can name ionic compounds. So for us to name ionic compounds, the cation is always named first before the anion. So the cation is always named first before the anion. So for this compound, this is a compound that is made from sodium and chlorine. So you are going to name it sodium chloride. So the name of the first atom remains the same, but the name of the anion, it is changed to ID. So this is sodium chloride. Let's look at the second example here. The two atoms that we have here are magnesium and the chlorine. So the name is going to be magnesium chloride. Now for this other compound, we have 2 ions here. We have the magnesium ion and we have the sulfate ion. So the name of this compound is going to be magnesium sulfate. Now, let's see how we can name these other compounds. Here, what you will understand is that copper has more than one charge. So there is copper 1 and there is copper 2. So the cation is always named first. In the first compound, we see that copper has a charge of 1 and chloride a charge of 1. So this is a copper 1 compound. So we are going to name it copper 1 chloride. For example 2, we see that copper has a charge of +2, that is copper 2. And the name of the compound is going to be copper 2 chloride. Now, let's look at this other example. Name the compound FeNO2 2. So one thing that you have to know here is that you must remember how to name this polyatomic ion. So the first here is ion, and how do we call this polyatomic ion? It's called the nitrite, as opposed to the nitrate that has 3 oxygens here. So the nitrite has 2. Now we are going to need 2 of the nitrite as shown by the formula, and for ion it means that we have ion 2+. So the name of the compound is going to be ion 2 nitrite. That is the complete name, ion 2 nitrite. Now let's look at a second example. Write the empirical formula for ammonium sulfide. So we said the empirical formula shows us the lowest whole number ratio. Here we have the ammonium ion. The sulfide has a charge of 2-. So for us to write the formula, how are we going to do? We must balance the charge. So this means that we are going to need 2 of the ammonium and 1 of the sulfide. And that gives us a formula of NH42, the 2 bracket affecting everything inside, then the sulfide. So that name is the ammonium sulfide. So let's look at the summary of the ionic compounds. We've said that ionic bonds occur between oppositely charged ions, and that in ionic compounds the total charge must be equal to 0. We've said we have to name them as the cation first and then the anion, and the formula name gives us the number of each of the ions that is found in that compound. Now let's look at the second part, which is covalent bonding. We've looked at ionic bonding, where we said this is the bonding between oppositely charged ions. Now for covalent bonding, we will see that covalent bonding occurs when electrons are shared between two atoms. In this case, it is not losing or gaining. Here, we talk of sharing of electrons for covalent bonding. Now, for example, we have two hydrogen atoms here. One, the Lewis structure here with one atom on the valence shell. The other Lewis structure here, one atom on one electron on the valence shell. So for it to form a covalent bond, they have to share their electrons. So you see here in the product that this nucleus and this nucleus, they have shared the two electrons that they have. This is the electron for this atom, this is the electron for this other atom. So they are now sharing the electrons. And when an electron is shared, you can either see it as indicated here or by just a single line as indicated here. So you see H dash H, that shows that it is a bond. So a bond is equivalent to two electrons. So this is the general way of writing out in the form of an equation here. So here, the hydrogen plus the hydrogen, they share their two electrons to either give you this or a bond, which is a hydrogen molecule. So by sharing the electrons, each hydrogen atom completes its valence level. Now, let's look at another example here. This is still the example that I've just demonstrated to you. So let's look at what happens for the hydrogen. We see that a hydrogen molecule, it will be diatomic, so it contains two hydrogens. We are going to look at the 7 rule, which shows you the 7 elements that exist as diatomic molecules. Now, let's see how the covalent bonding occurs in a fluorine molecule. In a fluorine molecule, remember we say one fluorine has 7 valence electrons. So we are combining two fluorine atoms here. So what will happen is that they are going to share their valence electrons. So when that happens, the two electrons are shared. So we have this electron and this other single electron. They share these two electrons, and that forms the fluorine molecule. So I've told you that this is equivalent to the same like a bond. So when you see that bond is two electrons, so a single line is called a bond, and it is equivalent to 2 electrons. This is the Lewis structure of the fluorine molecule. Now, this is what we call the 7 elements, the 7 rule. So the 7 elements form diatomic molecules. The magnificent 7 elements that form diatomic molecules are, so these elements, you will never see them single. Even if you want to write out an equation, hydrogen will always be diatomic, nitrogen will always be diatomic, oxygen will always be diatomic, fluorine will always be diatomic, chlorine will always be diatomic, bromine and iodine. So remember all these 7 diatomic molecules. I've told you that they will always be diatomic. For example, let me show you how the water molecule is formed. So hydrogen reacts with oxygen to give us water. So here you see that the hydrogen is always diatomic and the oxygen is always diatomic. Okay, so this is what happens. This equation is not balanced, so we put a 2 here. That gives us 4 hydrogen atoms and 2 oxygen atoms, so we put a 2 here. That balances the equation. So we have 4 hydrogen, 2 oxygen, and that is, so these are diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and iodine. Make sure you remember them. Now, these are the elements that we just cited, that they are diatomic molecules. They will always be diatomic. So let's look at double and triple bonds in Lewis structures. So we've just looked at the single bonds where they were sharing electrons. Let's now look at an example of oxygen to form because we've said these are the diatomic molecules. We've already seen the case of hydrogen, which forms just a single bond. We've seen the case of fluorine, which forms just a single bond. Now let's look at the case of oxygen. Oxygen will form a double bond and nitrogen will form a triple bond. So if we are looking at oxygen, oxygen is found in group 6 and it will have 6 valence electrons. So it's going to use 2 of each of the oxygens to form a bond, and that will form a double bond. So a bond here is 2 electrons, and the 2 are for all of the atoms. So if you count for this oxygen atom here, oxygen number 1, it has 8 electrons around it. So you count 2 for this oxygen, and you count 2 for oxygen number 2 for this bond and for this other bond. So each bond is 2 electrons, and you count for both of the atoms. Same thing for nitrogen. Nitrogen here, for nitrogen 1 and nitrogen 2, it forms a triple covalent bond. So it's formed by sharing of electrons. So nitrogen is in group 5, and it has 5 valence electrons. So what it's going to do is that it's going to use 3 of each of the nitrogen atoms that will share their 3 valence electrons. That forms 6. So here you have 6 plus 2, that makes 8 for this nitrogen. For this other nitrogen you have 6. Remember, this triple bond is 6 electrons, and they count for both of the nitrogens. Okay, so that makes 8 for both atoms. Now, covalent compounds fulfill the octet role by sharing their electrons, as we've already seen. Now, if you look at the water molecule here, in this water molecule, we have a pair of unshared electrons. There are 2 pairs, this one and this other one. So we have 2 pairs, and then for this bond, we have a pair of covalently bonded electrons. So we have this bond and this other bond. So we have 2 bonds and 2 lone pairs in water. Now, let's look at this question. In this structure, how many electrons does the nitrogen atom share through covalent bonds? How many of the valence nitrogen electrons are not shared? And does this nitrogen atom have a complete octet? Now, I want us to focus on the atom and start by stating the number of lone pairs and the number of bonds. So we have 1 lone pair, this is it here, and we have 3 bonds. Remember, we've said a bond is equivalent to 2 electrons. So each bond that you see around nitrogen is 2 electrons. So if you count all the 3 bonds, that makes 6 electrons, plus the lone pair, that makes 8. So the first question is, how many of the valence nitrogen electrons are not shared? So we have 2 that are not shared, that is for the lone pair. And now for the bonds, the nitrogen has 6 shared electrons. Remember, each bond is 2 electrons. So you have 3 bonds, that makes 6 shared electrons. Now we have the lone pair, that is 2. So if we sum all of these, because the last question is, does this nitrogen atom have a complete octet? So we have to sum all the electrons around the nitrogen. That is going to be 6 plus 2. That gives us 8 electrons, and it means it has an octet. Now, let's look at molecular formula. I told you about the empirical formula and the molecular formula. The empirical formula shows the lowest whole number ratio, and the molecular formula shows you the actual amount, the actual number of atoms in the molecule. For example, here we see a molecule here, and we see the molecular formula and the empirical formula. For the molecular formula, it shows you that you actually have 2 nitrogen atoms and 4 hydrogens. The empirical formula shows the smallest whole number ratio. So you will have NH2 for the empirical formula. Now, let's look at the structures of the covalent compounds. So covalent compounds, they often have complex structures. For example, we are looking at this hydrocarbon here. All the fuels that we use, the hydrocarbons. So this is an example. So we see that they are complex. Now, how do we name these covalent compounds? So I'm going to just show you how we name these, and then in the next slides I will show you how to bring out the name. So we have the compound here, phosphorus monoxide. We have PO. We have diphosphorus trioxide. So di here shows that we have 2, and then tri for oxygen. Trioxide means that we have 3. We have diphosphorus tetroxide, means we have di 2 for phosphorus, tetroxide 4. For tetraphosphorus decoxide, tetra means 4 and deca means 10. Alright, Now, name these binary covalent compounds. Binary means 2. So, this is a covalent compound that is made up of 2 atoms, phosphorus and chlorine. So, how do we name these compounds? We have PCl3 and PCl5. How do you name these compounds? So, let's start. On the periodic table, the atom to the left is named first. So, for naming covalent compounds, the atom to the left is named first. And then, the atom to the right is named as an anion. So, here, it is going to be phosphorus. And then for the other atom, it's going to be like chloride. So this is phosphorus trichloride. Tri because we have 3 of them. Now let me show you a table that shows you if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, how do you name it? So when you have one atom, it is mono. When you have 2, it is di. For example, if you have CO, that is carbon monoxide. Okay, so when you have 1 is mono, when you have 2 is di, when you have 3 is tri, when you have 4 tetra, when you have 5 is penta, when you have 6 is hexa, when you have 7 is hepta, when you have 8 is octa, 9 nona, 10 deca. Now we have named the first compound here, phosphorus trichloride. Let's look at the second compound. Now when we are naming these compounds, for example, we omit for the first element, we don't say the mono. For the mono here, for example, you don't say monocarbon monoxide. You omit the mono for the first element. That is the only exception. If it was di, you must name it. Now, another example here, if you see this is carbon disulfide. You don't say monocarbon disulfide. That is what we mean you omit for first. With the star here shows that you omit for first element here. So you don't say it's monocarbon disulfide. You say it's carbon disulfide. Di because there are 2 of them. Now, let's look at the last compound that we've given here, PCl5. PCl5 will be called phosphorus pentachloride because we have 5 of the chlorides that will make pentachloride. So, phosphorus pentachloride is PCl5. Now, when we have P2O5, P2 means that 2 of the phosphorus. That means it will be diphosphorus. Then for the oxygen, we have 5 of them. That will be diphosphorus pentoxide. Normally, you would have said pentaoxide. But when you are naming a compound that has a vowel, like for example, oxide, it's going to be just oxide. You remove the A on the penta, or even if it is tetra, okay, or even if it is deca. For example, we saw P4O10. So this normally will be tetraphosphorus decaoxide, but you have to remove that A in that deca, and that becomes tetraphosphorus decoxide. So you see that the A here, it does not apply. Decoxide. It's not decaoxide. So once the name begins with a vowel, you omit the A. Now, practice naming these covalent compounds. You can pause the video here, and then you name these compounds. So, the first compound here is going to be nitrogen dioxide. So remember, we don't say mononitrogen. We just say nitrogen dioxide. The second compound is going to be dinitrogen. We have 2 of the nitrogens, dinitrogen, and we have 4 of the oxygens. And we said when the compound begins with the vowel, we omit the A. So this is going to be dinitrogen tetroxide, not tetraoxide. Dinitrogen tetroxide. Alright, so let's look at the summary of the covalent compounds. We've said in covalent compounds, atoms share electrons to attain the octet. We've said the covalent bonds form between non-metals. So you will never see any metal involved in the covalent compound. All metals are ionic compounds. So the most covalent compounds form discrete molecules, and we describe molecules using the Lewis structure, as we've shown. Now, we will get to chapter 9, and in chapter 9, we'll talk more about the Lewis structures. So we describe molecules using the Lewis structures, using the molecular formulas, and naming binary covalent compounds. We've said you name the element first, which is the leftmost, and then the second element named as an anion. And the prefixes indicate the number of atoms present. Now, let's distinguish between ionic and covalent compounds. The first thing I've told you is that covalent compounds are formed only between nonmetals, and ionic compounds are formed between nonmetals and metals. So that is the first difference, and that you must remember. So to fulfill the octet rule, atoms gain or lose electrons and they form ions, and the other atoms share electrons to form covalent bonds. So covalent compounds share electrons between non-metals usually, and they form molecules. An example of such a molecule here is N2H4. Alright, let's look at the ionic compounds. The ionic compounds, they are formed between oppositely charged ions, that is a cation and an anion, and they don't form molecules. They form what we call formula units or empirical formula. So covalent compounds will form molecules and ionic compounds will form formula units. So you cannot say a molecule of sodium chloride. You say a formula unit of sodium chloride. Alright. Now, properties of ionic and covalent compounds. For example, here we have limestone. Limestone here is an ionic compound. It is formed between calcium and the carbonate ion. So olive oil here is a covalent compound that is formed between two non-metals. So covalent compounds and ionic compounds, how do you identify them? So all of the covalent compounds are non-metals, and all the ionic compounds are metals and non-metals. So they contains polyatomic ions. For example, identify these compounds as ionic or covalent and name each one. Let's look at them. MgF2. So you can pause the video here and first of all identify if these compounds are ionic or covalent. Then the next thing, you name them, because we have seen how to name ionic compounds and how to name covalent compounds. Now, the first one is ionic, that is magnesium fluoride. The next one to the right is covalent, formed between phosphorus and oxygen. Those are all nonmetals. Now, how do we name that compound? We name it diphosphorus tetroxide. Now, the third one here is ionic, formed between iron, which is a metal, and the nitrate, which is an anion. So, how do we name this compound? This is iron 3 nitrate. Now, the last compound here is formed between sulfur and chlorine. That is a covalent compound. Okay, because sulfur is a non-metal, chlorine is a non-metal. So how do we name that compound? Sulfur hexachloride. Alright, so let's look at aqueous solutions. Aqueous solutions, everything that you put into water, that is aqueous solution. So that is a solution where water is the solvent. An aqueous solution is a solution where water is a solvent. Now, how ionic and covalent compounds differ in aqueous solution. Now, aqueous solution, we have said, is a homogeneous mixture in which the main component is water. Water is called the solvent, and the other thing, the solute, is what is dissolved in the solvent. So when we say it is soluble, when we say a substance is soluble in aqueous solution, it means that it is able to dissolve. Now, let's look at electrolyte solutions and non-electrolyte solutions. So electrolyte solutions are solutions that are ionic compounds dissolved in water. So when an ionic compound is dissolved in water, it forms an electrolyte solution. Here, for example, in this last beaker, that is an electrolyte solution. Here, in the first beaker, we have just pure water. Pure water does not conduct electricity. So that is why you see the bulb here doesn't light up. Here in the second beaker, we have sugar. Sugar is a molecular compound, and molecular compounds, they do not dissolve in aqueous solution. So they just remain in that state. They don't dissolve. So they don't form ions. Now for ionic compounds will dissolve to form the ions. And because of the ions make it possible for the solution to conduct electricity, because we have positive and negative ions in solution. So dissociation means that when you put in a substance in water, it breaks down into its ions. So dissociation means that the ions are pulled apart in aqueous solution. Here we have salt, which is sodium chloride. This is the structure of sodium chloride here. You see it is intact. Here we have water. We know that the water molecule contains 1 oxygen and 2 hydrogen. So here we have the water molecule. Now when we dissolve salt in water, what happens is that it dissociates into sodium ions and chloride ions. Now the water molecule, we know that the oxygen in the water molecule is partially negative. Okay, and we know that unlike charges will attract, so the negative and the positive will attract. So we see that since the sodium is positive, it will be attracted by the oxygen, which is negative. So that is what is happening here. The sodium is attracted by the oxygen, which is negative. Now the chlorine is negative and the hydrogen in water is positive. So here you see the hydrogens are the ones surrounding the chlorine. All right. Now let's look at acids. What are acids? We've said that the covalent compounds, they do not dissociate in aqueous solution. But an exception that we'll see is that acids, they are covalent compounds and they produce hydrogen ions when they are dissolved in aqueous solution. So acids are covalent compounds and they will produce hydrogen ion in solution. So that is an exception for the covalent compounds. So the first acid here is called hydrochloric acid, and it will dissolve to form the hydrogen ion and the chloride ion. For nitric acid here, we dissolve to form the hydrogen ion and the nitrate ion. So these are the common acids that you should know. So we have hydrofluoric acid, we have hydrochloric acid, hydrobromic acid, hydroiodic acid, and carbonic acid. So we also have nitric acid, nitrous acid, sulfuric acid, phosphoric acid, and acetic acid. Now, all acids are corrosive. So you have to be always careful when you're working with acids. Now let's look at binary acids. Binary acids, when you hear of binary, it means 2. So we are looking at acids that are formed from 2 elements. So all the binary acids that we have are the acids formed between the halogens. We have hydrofluoric acid, we have hydrochloric acid, we have hydrobromic acid, and we have hydroiodic acid. So how do we name these acids? We name them by putting hydro, then the root name of the element, and then we add IC plus acid. So hydrofluoric acid, for fluorine, we put hydrofluoric acid. Same thing for chlorine, hydrochloric acid. Now let's look at the oxy acids. Oxy acids are acids that contain oxygen. So they form hydrogen ion and an oxy anion. An example of this is the nitric acid. So let's look at the ones that have ATE, like the nitrate ion. So they will become IC acid. For nitric acid, it is the nitrate. So the ATE will change to IC, then we add acid. So for the nitrate, we'll add hydrogen to it and it becomes nitric acid. Okay, for carbonate, we'll add hydrogen and it becomes carbonic acid. So the carbonate becomes carbonic acid. So for the sulfate, it becomes sulfuric acid, and for the phosphate, it becomes phosphoric acid. So that is how we name the oxy acids. Now let's look at the oxy acids here with different number of oxygen atoms. We just saw the nitrate. Now let's look at the nitrite. We also saw the sulfate. Now we are looking at the nitrite here. The nitrite, the ITE will be converted to OUS. Then we add acid. For example, the nitrite will be called nitrous acid. The ITE is converted to OUS to give us nitrous acid. Here we have the chloride. It's going to be chlorous acid. Now, the summary of electrolytes, we've said electrolytes can be ionic compounds, in which case the cation and the anion will be formed in solution, or electrolytes can be acids where the hydrogen ion is formed in water. So that is the end of this chapter.